Namaste, welcome to unit number 2 of Power System 1 course, which is Power System Components. Okay, in this unit number 2, we are going to discuss about the various Power System components. Specifically, we are going to discuss about the parameters of transmission lines, and also we will discuss about the modeling of transmission lines, because whenever you want to analyze the transmission network, you need to have mathematical models. Okay, so we will be discussing about the mathematical modeling of transmission lines and the steady state, and then we will be discussing about the characteristics of transmission lines, and in the end we'll also discuss about the series and shunt reactive power compensation of transmission lines. Okay, this is what we will be discussing in unit number 2, and in this particular learning dialogue I'll be discussing about the parameters of transmission line, and then we'll start with the first parameter, that is how to calculate inductance of the transmission lines. Okay, let's move on. So first one is transmission line parameters. Okay, so what is the purpose of a transmission line? Okay, as we already seen in the previous videos, the resources and the load centers are far away from each other, so you need to transfer the electricity from the resources place to the load centers. Okay, because the transportation of resources is costlier compared to the transportation of electrical energy. Okay, so we require transmission lines to transport electrical energy from the resource place to the load centers. Okay, so obviously we use the aluminum conductors for transmitting power from one place to the other place. Okay. So basically you can say your transmission line is just like a current carrying conductor, which transfers energy from one place to the other place, transports energy from one place to the another place. So it can be treated as a current carrying conductor. And as you all know from the fundamentals, every current carrying conductor is associated with two things. One is the magnetic field and electric field. Okay? The magnetic field will be surrounded around the conductor, and the electric field will be existing between the conductor and the low potential point. Normally in transmission lines, it is the ground, okay, earth point. Okay, so electrical field will be existing between your conductor and the earth. Okay, and magnetic field is surrounded by the conductor in circular path. Okay, and in addition to, and because of these two fields, the every conductor is associated with inductance and capacitance. Okay, since it is associated with the magnetic field and there will be some energy storage in the magnetic field, that we will represent as parameter inductance. Okay, and whatever the energy that is stored in the electrical field, that physical phenomena will be represented as capacitance. And in addition to these two, we also have one more parameter that is called resistance. It is because of the property of any material. Okay, if you consider, if you take any conductor, it will have inherently a resistance property which will oppose the flow of current. So this is one more parameter that any transmission line will have. Okay, so these are the three parameters, and in addition to this, we will also have one more parameter called as conductance. But this conductance is due to the leakage currents from the transmission lines to the edge points. That could be either tower to which these transmission lines are hung, or any other insulating material. So the conductance is going to represent the leakage currents from the transmission lines to the edge points. Okay, and these when compared to the other parameters, this is very small, so we will not be consider discuss much about this conductance during this unit number 2. We will be mostly concentrating on these three parameters, that is resistance, inductance and capacitance. And out of these three parameters, the inductance parameter is predominant compared to the resistance and capacitance. So these are the four parameters that any transmission line will have: inductance, capacitance, resistance and conductance. Okay, so these four parameters we are going to have for a transmission line, and here we are going to start with inductance. Okay, let us see. Let us start with the definition of inductance. and we will also discuss how to calculate this inductance for a given transmission line. Okay, so how do we define inductance? Okay, if you consider any conductor, the voltage induced in the circuit is given by, this equation, that is E is equals to rate of change of flux linkages. Rate of change of flux linkages. Whenever there is any change in magnetic field, there will be some induced EMF in the conductor. Okay, so that is represented in the mathematical form as E equals to d psi by dt, where psi is the flux linkages of the circuit in Weber terms. Okay, so if you rewrite this equation by multiplying the numerator and denominator with the di, okay, so we are going to consider define this ratio d psi by di as inductance. Okay, so inductance is defined as change of flux linkages with respect to the change of current. Okay, that is the definition for inductance. Okay, so we have derived this inductance from the fundamental equation, that is E equals to rate of change of flux linkages. Okay, so this equation is going to be E equals to L di by dt, where L is going to be d psi by di. Okay, and this we will define it as inductance, and the unit of this inductance is Henry. Okay. So if you consider a linear magnetic circuit where flux linkages are constant, that means their flux linkages vary linearly with current. Okay, with respect to current, if they are varying linearly, in that case, what we will do is we will represent inductance as psi by I, where all these are constants. Okay, they are not time varying. Okay, this psi is going to vary with respect to current in a linear manner. Okay, and then the same equation, if you want, you can also rewrite as psi, the flux linkages can be calculated as inductance into current. Okay, so if you know the parameters of your flux linkages and current, then you can easily calculate the inductance. Okay, so we are going to make use of this equation L equals to psi by I in the coming videos to calculate the inductance. So if you want to calculate the inductance, first you need to calculate the flux linkages. Since we can easily measure the current, if you know the flux linkages, then simply by taking the ratio of flux linkages with current, you can easily calculate the inductance. Okay, this is the scenario when your magnetic circuit is linear. That is, flux linkage vary linearly with the current. Okay, if it is uh, current is alternating, okay, then we are going to represent the same equation. Instead of psi, we will use this lambda. We will represent it as lambda equals to L into I, and I is also a time varying quantity. Okay, so in the same fashion, in the voltage drop due to the alternating flux linkages in sinusoidal steady state, we will represent it as V equals to J omega angular frequency into inductance into I. Okay, so this L into I can be replaced with the flux linkages from this equation. So voltage drop due to this alternating current in will be J omega lambda. Okay, so this is whatever inductance that you have defined till now, that is called as self-inductance. Okay, that is formed because of the current passing through the same conductor. Now, in addition to this, we also have one more inductance. We'll call it as mutual inductance, and this is going to exist between any two circuits which are very near to each other. Okay, so in this case, the mutual inductance is defined as the flux linkages of your circuit 2 with circuit 1 divided by the current passing through the second circuit. Okay, so this is the mutual inductance is because of the current passing through the neighboring circuit. It's not because of the current passing through the same circuit. Okay, so this is going to exist only when you have two current carrying conductors nearby each other. Okay, and the voltage drop in circuit 1 due to the current in circuit 2. Okay, what are the voltage drop that you have defined here? V equals to J omega lambda. That is because of the current I that is flowing through the same conductor. But here, whenever you have any mutual inductance existing, then what happens is the voltage drop in the first circuit will be due to the current in the second circuit, and that will represent as V1 equals to J omega M1 to I2, or simply it is J omega lambda 12, where lambda 12 is M12 into I2. Okay, so this is how we'll define the inductance and mutual inductance. In the coming video, we will be discussing about how to calculate this inductance. Okay, thank you.